Brian Jones, one of the applications engineers here at Unitronics. Joined, of course, by Mike, Dan, and Alex. If you have any questions at any time during the presentation, please feel free to type in the chat window. They can get to you as soon as they can. Today we're going to be talking about CANOpen, one of our CAN bus protocols for communicating with CANOpen devices. CANOpen is definitely a very feature-rich protocol. It has a lot of bells and whistles, so to speak, that you don't see with normal protocols. One key feature is the data can be sent in order of importance. So we can give the most important data, for example, maybe an alarm or an error message, a higher priority, and it will always be sent before any other messages. The same token, we can also give a message an extremely low priority, and it will always be sent last. This is all taken care of on the device side. This isn't something we actually have to code in ladder. This is something taken care of on the device and all automated. There is a standardized object directory with each CANOpen device. It's commonly found in what's called an EDS file. We'll take a look at one of those in a second. This is going to have all the information you need to work with the device. It's going to have all the addressing information for you. It's going to have all the communication parameters. Anything that you need to read or write to the device is going to be located in the object directory. It is standardized. There is also a group of common commands that we can send that are universal across all CANOpen devices. So if you know your way around one CANOpen device, you'll be able to operate around another. It's fully customizable. We can set up how frequently data is sent or received. We can configure the communication parameters while the device is running instead of through a dip switch like we normally would have to. It's actually a ton of little hidden features that are available to you. Most of them are optional. They're not required. So I will show you how to hook up a CANOpen device as quickly as possible, just getting the reading that we're looking for, as well as show you some of the cool things we can also do with it. And of course, this is a CAN bus protocol, so we have to follow our proper wiring. We do require there to be a separate 24-volt DC power supply powering the cable. You should not share it with the power supply powering the PLC. This should just be for the cable itself. At each end, similar to all our other CAN bus wirings, you are going to have a 121 ohm terminating resistor at each end. So for example, on my desk here, I have just a Vision 570 hooked up to a CANOpen shaft encoder, and I have a terminating resistor on each of them. If I had a third device in the middle, I would only put them on the two ends. The cable, of course, is a standard device net cable. The resistors as well, they are included in every CAN capable device we sell. It should be included in the box. If not, it's just a regular 121 ohm resistor. As I mentioned, there is an object directory for every CANOpen device, and it's going to have all the key information we're looking for. The main descriptors that you're going to find in there is, first is the index. This is the physical address of the information that we're looking for, similar to a Modbus slave address table. Next is the object type. Is it a single variable? Is it an array of variables? Maybe it's an ASCII string. Next we have the name. This gives a description of what the operand actually is used for. Next up is the data type. For example, an unsigned 32-bit register, or as we like to call them, a double word. It will tell you the attribute of the operand. It is either read-write, read-only, or write-only. It'll tell us what kind of permissions we have. And of course, it'll also tell us the default value if there is one. Now also with every CANOpen message, before every message there's always going to be what's called the COB ID, short for Communication Object Identifier. What this does is it does two things. First, it's going to tell us which function we're going to run. Are we asking for information? Are we changing the state of a machine, etc.? We'll go over all the different command types in a moment, as well as which node we're actually communicating to. It's an 11-bit ID code. The first 4 bits are the function code, what type of command it is, and the last 7 bits is the node number. So for example, function code 0011 in binary, that's request PDO. On node number 2 would be 182 hex. Just by adding the two together and converting from binary to hex, I get 182. If you put in node 0 as your node number, it will be a broadcast, meaning it will go to every device on the CAN bus network. The value of the COB ID also determines the priority. So the lowest numbered COB IDs always go first. So this works twofold. One, the function codes are prioritized. Since the function code goes first, the lower the function code, the lower the converted number is going to be. So the functions are put in a particular order that the most important functions always go first. Second, after the function code is organized by the node number. So node 1 always gets update first, node 2 second, node 3 third, etc. All right, the first function code we're going to take a look at is called NMT, short for Network Management. This is how we can change the current state of a device. So if we start at the top here, this is considered power up. So the first thing a CANOpen device is going to do on power up is, of course, initialize, setting any COM parameters or any default values. And then it's going to go into what's called pre-operational mode. Pre-operational mode is when we can program the device with the settings that we want for our system before it actually starts running. After it's in pre-operational mode, I can then turn it into regular operational mode, which is the regular running state of the device. At any moment, I can stop the device, and it goes into what's called prepared mode. The device will keep any settings that I have programmed into it, but it's going to stop sending out data unless requested. To get the device to start shooting back data again, I'll have to put it back into operational mode. And this little flowchart here just shows you how to get from one to the other. The COB ID for NMT commands is actually always 0. Instead, the node number is stored in the message itself. So an NMT command is going to be 2 bytes. Byte 0 is going to be the command, and byte 1 is going to be the node number. For example, command 1 on node 2 would tell node 2 to go into start mode or change its state to operational. There are 2 extra ones I want to point out, 129 and 130. The numbers are not super important because in VisiLogic this will all be taken care of automatically for us using the function blocks. But it is important to understand what is working behind the scenes to just get a better understanding of what's going on. So 129 and 130 are the 2 different resets that we have. Reset node is going to reset the device entirely. It's going to go back to all its factory defaults. If I put in any set points or any custom values into the device, they're all going to go back to their factory defaults. The second, command 130, is only going to reset those variables that are needed for communication. So if I set the baud rate on the device or perhaps I change the node number. Reset communication will only reset those values. Next we have sync. The sync command will broadcast a heartbeat to all the devices on the CAN bus network. And the devices can be programmed or configured on how to respond to those heartbeats. Oops. For example, I could say that on every sync, I want every device to report back its current values to my master controller. I could have one always report back on every sync. As well, I could have a second device that only reports on every fifth sync. So you can set the timing using the sync. As well, one of the key benefits of CANOpen is when you do the request using the sync, you'll get all that information at the same time. Normally with example Modbus or Modbus IP, we have to connect to each device individually, and we will go in order, so 1, 2, 3, 4, 5, etc. With CANOpen, we get all that information at the same time. Everything is synced up to a heartbeat. Next up is the emergency codes. It's commonly used for error messages if there's ever anything wrong. If there's perhaps a power failure, short circuit, anything that the device detects as a problem, it's going to send us an error code. We can find in the object directory what that error code actually means and what the problem was. And next up is PDO. This is the most important one. This is actually how we're getting the bulk of our information. So for today's example, I have a CANOpen shaft encoder that's measuring position. Every time the position change, it's sending out a PDO. PDO is a packet of all the vital information. So in PDO1 here, there's actually 3 different ways I can configure the shaft encoder. The default PDO configuration is just to send me the position. So here's the layout of the message. Of course, I always start with the COB ID, and then I get 8 bytes. With the default PDO, the first 4 bytes of that message is going to be the position. I have the option of changing that. I can program it instead that the first 4 bytes will be the position, and the 5th byte is actually going to tell me if certain set points have been reached. So I can set 4 different set points. I will get a 4-bit bitmap telling me which one of those positions has been triggered or not been triggered. Lastly, type 2 is what I actually have it set at right now. The first 4 bytes will be the position, the next 2 will be the current speed, and the last 2 will be the current acceleration. The contents and the trigger can all be customized. So as you see here, here's the 3 different options for the contents. As well, the trigger can be programmed. Right now I have it sending whenever there's a change. If I wanted to, I could have it be sending off of a sync or every 3rd sync. As well, I could also set it on a time schedule. So every half second, every second, etc. Whatever I program into the device is how it's going to report back, or when it will report back. SDO, or Service Data Object, this is how we're going to do with the bulk of our programming to the controller, whereas the PDO is a prepackaged set of data. That's the most important data. The SDO is more of an a la carte method. We're just addressing a particular register that we are either sending to the device or requesting to read from the device. And again, so for example, using the flags on the shaft encoder, this is how I would program in the set points that I plan on using. This is how I can also tell it which PDO style I want to use, the default, the type 1, or the type 2. This is all done using SDO commands. A little bit of terminology, of course. If we're going from the PLC to the CANOpen device, that's considered a download SDO. If I am requesting to read information off the CANOpen device and upload it to the 570, that's considered an upload SDO. And lastly, we have NodeGarden. If anyone's familiar with Unican, we have a feature called Check Alive that we use to determine if a device is still on the network. NodeGarden is a similar technique for CANOpen. We can simply ping or test to see if a controller is still connected and online. And if it is not in our ladder, we can then no longer request or send data to that node. All right, so here's a chart breakdown of all the codes we just mentioned, going in order of priority by their COB ID. So of course, the first one, COB ID 0, is changing the state of the machine using NMT. Next, we have the sync. After that, we have a timestamp. It's possible for all the controllers to share a UTC timestamp. Next, we have the emergency. There are 4 PDOs, and a transmit and receive for each. Then the SDO transmit, SDO receive, and lastly is the NodeGarden. Again, everything goes in order of the COB ID, so the PDO 1 has a higher priority than PDO 4. All right, so now let's open up VisiLogic and we'll see how to configure our first device. All right, so I have a quick sample program here from my shaft encoder. Like with all communications, the first thing we want to do is have an SB2 power-up bit to initialize the PLC for the type of communication we're going to be using. Because it is going to be part of the CAN bus network, it does need a PLC network ID. In this case, I've just defined it to ID 1. Next, I need a common init. I'm initializing the COM port to CANOpen, setting the baud rate to 250 kilobytes. Basically, just have to make sure the baud rate matches what I have set up on the encoder. And next we have the CANOpen configuration. This is where we're going to do the bulk of our configuration. So go ahead and open that. This, of course, is found under COM and CANOpen. All the CANOpen function blocks are going to be in this drop-down here. All right, so this is the CANOpen configuration. First thing you'll notice is the giant block of all the different nodes, labeled 1 through 27. Each node is going to get its own configuration. I currently have my encoder set to node 2, so to configure it, I just click on node 2, and then I can define my parameters on the window below. The first tab here is the emergency information. So if I get an error code from the node 2, it's going to be stored into MI 1000 on my master controller. The register that the error code is about will be stored in MI 1001. Next, I'll have some data. This is all manufacturer specific, so I would have to look at the documentation of the device to see what these next bytes will mean. And of course, I also have a receive bit that lets me know that an emergency message did come in. Click on the next tab here to look at our NMT commands. These are our network management commands. When I request to change the status of a node 2, it's going to report the current status back to me, and it's going to be stored in MI 1003. And of course, as soon as it does, memory bit 1003 is going to go high to let me know that it did. Of course, the most important piece of data is going to be the PDO. Like I said, this is where the most important data is. For the shaft encoder, this is the position. If it was a pressure transducer, this would be the pressure reading. If it was a temperature device, it would have my temperature. Whatever the device is actually reading is always going to be in the PDO. So this is the most important. You'll see that it automatically, when I click the checkbox in the PDO, it automatically populates the COB ID. It gave us the number 182. That's because PDO1 is function code 180, and I'm on node 2. Add the two together, and I get 182. It's in hex, by the way. As soon as that PDO1 comes in, MB 1004 is going to go high, and it's going to store it into MI 1100. It's going to be in 8 bytes, and I have a vector length here of 8. If I wanted to receive the second PDO, third PDO, or fourth PDO, all I would have to do is click the checkbox, assign the receive bit, assign where I want the data to be saved, and put in the message length. The message length is going to be found in the documentation for the device. The last tab is for transmitting PDOs. This encoder that I have does not have that feature, so you'll see it notices blank here. But if you do have a device that has the ability to receive a PDO from the controller, this is where you would configure it here. Now, in the previous versions of VisiLogic, we only had 4 PDOs available. Because at the time when it was made, there was very few controllers that had any more than that. We are starting to see a couple more, so in the latest revision of VisiLogic, we've now added the ability to assign an indirect COB ID. If you do have, for example, a device with PDO 5, 6, or 7, you can just click the relocate PDO. And you can manually type in the address of the PDO. So PDO 5, I could just type in 582. All right, so first I want to show you the program running so I can show you the differences between the PDO and the SDO, and then we'll go through the function blocks that operate them. Okay, so here's the HMI screen I have set up. You'll notice that right now the shaft encoder is in pre-operational mode. So if I turn the encoder, I don't see the position change at all. The encoder is basically in stop mode. If I hit start, and I send it the NMT command to go into operational mode, now when I turn the encoder, you can see the value change. I have the position being stored into my first numeric, and then the velocity and the acceleration. This is all being grabbed from the single PDO. I'm just dividing the first 4 into the position, and then the last 2 into velocity and acceleration. So the PDOs are sent automatically. I do not have any function blocks in my ladder that are requesting to read the PDO. As soon as I make a change on the encoder, it's just automatically sent to my PLC. That is all customizable and programmable. I could have set it up differently. I could also do what's called a PDO request to read, where I could just, similar to a Modbus read, just grab that information when I request it. And now I'll show you how the SDO works. So I have a little setup window here where I can directly send a download SDO or an upload SDO based on its index, subindex, and the length. You'll find all the index information in what's commonly called the EDS file. We actually have a built-in EDS File Viewer in VisiLogic. If you click on Tools and then click on Uni-EDS, I'll show you what the EDS file for this encoder looks like. So this is Uni-EDS. By the way, this EDS file is also available inside of VisiLogic. If you just go to the examples directory in communication and CANOpen, this is the encoder project, and we have the EDS file along with it. So if you want to experiment and take a look. So when you open it, this is what it's going to look like. So if I click on, we're going to go to the preset value, which is this guy here. So the preset value is basically the home position for the encoder. This is where 0 is going to be. You'll see first is the subindex and the index. The index is the memory location. So if I wanted to change the preset value on this encoder, I would have to address it using the index. Now there's only one value here, so the subindex is 0. But if there were multiple values, you would see subindex 0, 1, 2, 3, etc. In fact, I'll open one real quick that does. This is the PDO communication parameters. You'll notice that the index is the same for all 4, except as a subindex for each one. So it is possible to hold multiple registers or operands in a single index. So if that is the case, we just need to also include the subindex. I see that the object is a variable. I know that it's the preset value. I know that the data type is an unsigned 32-bit register. So if I am going to try to send a value to it, I of course want to use a double word. I see that the default value is 0 and that the access is read and write. So if I go back onto my PLC, and I put in index 6003, that's the preset value. So I'm going to keep the subindex at 0. The value to send is going to be 0. Basically going to zero out the encoder. Length of 1. And then I hit download. Now if I go back, you'll see it's been zeroed out. Next, we'll do the upload SDO. So if I go back into my EDS file and pick a value that I want to read, let's get the node ID. Now I have the dip switches set to 2, so I can check to make sure that the response back is 2 as well. So again, the first thing I look for is the index. It's going to be 100B. Subindex is 0, and the data type is double word. So back in my program, I already have it entered here. Just zero this out. If I request to read 1000B, subindex 0, length 1, I get node 2. For some reason it's not showing up. Anyway. All right, now I'll show you the function block I did use to get these. Now in this program, what I have it doing is as soon as the controller powers up, it's immediately sending an SDO to the encoder to tell it that I want to be in type 2. Remember from the presentation, type 2 is position, velocity, and acceleration. So as soon as the controller powers up, I do have a slight delay to make sure that the CAN bus is also configured and initialized and ready to go. So after 0.1 second, I have a system bit to make sure that the SDO is not in progress. This is system bit 242. Like all of our communications, we always want to make sure that the channel is available before we call on it. And then I have the SDO function block. The first input is going to be which node we're looking for. I'm looking for node 2. What is the object index? Here I have 2005. I'll show you real quick in the EDS file. So 2005 is the PDO mapping. And from the documentation that I got with the encoder, I know if I put particular values in here, it will change how the encoder is operating. There is no subindex, so I leave the subindex at 0. It's a domain segment transfer. We also have block transfer, but for this encoder, everything is set to domain. Now I select what values from my controller I want to send to it. So it is sending MI 1050 with the power up value of 2. 2, of course, puts it into type 2. I have the SDO array length, and I can set a timeout in units of 100 milliseconds. All this information I was able to find out using the EDS file as well as the documentation that came with the encoder. So every time they turn on the PLC, they won't have to reconfigure the encoder every time. It's just always going to power up in type 2. All right, now I'll show you how I change the status. So I had the 3 buttons on my HMI screen to determine if it was in stop mode, pre-operational, or start. These are just the NMT commands. Send NMT control. Their busy bit is system bit 292, so I want to make sure that there's no other NMT command currently in operation. If not, go ahead and open it up. Very simple. We just say what node we are referencing and what state we want to put it in. Start, stop, pre-operational, reset, or reset communication. You'll also see the function code on the left there, 1, 2, 128, 129, and 30. Luckily though, VisiLogic takes care of all the formatting for us, so we can just use the drop-down to select the right one. So I just have a button for each different state. Start, operational, and stop. I've also incorporated a NodeGarden to let me know if anything goes wrong on the controller. To initiate the NodeGarden, you actually have to send the request to the controller. So I'll actually start on the bottom part first. So this is the send NMT NodeGarden. This is going to basically ping the device and see if it gets a response. If I do not get a response, I'm setting MB103. If I don't get a response within a half a second, I know that there's a communication problem. To alert the user, I've simply just have on my HMI screen the NMT status as a text by pointer. And I've set 255 to be no communication. The reason why I chose 255 is because it's not used by any of the other NMT commands, so it's available. These are all determined by the encoder itself, not from my ladder logic. So if the encoder is initializing, it's going to send me a 0, disconnected 1, connecting 2, etc. These are all defined by the encoder and not my logic. So I added one for 255. This is the only one that's actually determined by the logic, and this one tells me that there's no communication. So if I go back online with the controller, and I disconnect the CAN bus cable, I see no communication. As soon as I reconnect the cable, it goes back into pre-operational. If I hit start, it's back up and running. You don't necessarily have to, of course, have a start button. This is just purely for example. In most cases, you're just going to want the PLC to fire up and immediately start reading off the encoder. So the start command can just be automated in ladder. You would just have it as soon as the controller powers up to then wait a second and then send the start command. Now, one thing you're commonly going to see if we go back to my slide. Oops. All right, so here is the PDO that comes in. It's just going to come in a packet, basically this 8-byte chunk of data. It's up to me to then use it accordingly. So right now that I have it in type 2, the first 4 bytes is going to be the position, which of course is a double word. The next 2 bytes is speed, and then the last 2 is acceleration. When it gets received in the controller, though, I have it linked to MIs. So this is going to be stored into 4 MIs, not a double word and 2 MIs like I need it to be. So in my program, I'm going to have to tell it how to use these first 4 bytes. To do that, I simply just wrote a small routine here using the copy memory function. So this MI 1100, this is where the PDO was received. I'm going to then store the first 4 bytes. So MI 1100, 1101, 1102, and 1103. I'm going to take those, it'd actually be 1100, 0, and 1001, because it's 2 bytes per MI. So I'm going to take those first 2 MIs, and I'm going to store them into double word 100. The length here is in bytes, not MIs. So I can quickly and easily just convert the 2 MIs that were for position into 1 double word, so I can properly view it on the HMI screen. The same would be done if it came in as a memory long, a signed 32-bit register, or if it came in as a bitmap. I would have to convert it from the MIs that I received them in into their proper designation.